let's begin. All right, well, it's another week and a snowy Monday. Thanks for braving the storm. It turned out to be a little bit of a much to do about nothing, but anyway, I'm happy that you're here. Hopefully you are too. Anyway, our problem to kick off today is cancer screening. Okay, so a relevant problem to many of us, and maybe will eventually be relevant to many of us if it's not already. Anyway, so suppose you take, or somebody takes a test for cancer. Here's the particulars for the test. If the person has cancer, it will report yes for cancer 90% of the time, 10% no. Okay, so 90% sort of accuracy, and likewise, if the person doesn't have cancer, there's a 5% chance that it will actually report that they do. Okay, so 95% accuracy on no. Okay, now if you don't know anything, the patient in question has an incidence rate of 1%, so 1 in 100 chance. And suppose such a person, no family history, takes a test and it gets positive. So what's the chances that they have cancer? Okay, so we're going to apply the method. I think we're sort of getting good at this now that you're largely going to do what's going on here. Okay, so we're going to do the setup. Okay, but I'll get you started. Okay, so that we're all speaking the same language. So normally we define the two events. Okay, so there's two events. The person has cancer. So let A be the event that person X has cancer. And B is going to be the event that X tests positive. Okay, the first thing that we should do is go through the problem and find all the information from the problem that we know. Okay, let's start here. Okay, for patients with no family history of cancer, the incidence of cancer is 1%. What does this tell us in terms of the events A and B? Okay, so the probability of A is 0.01. The probability of B, I'm not too sure. Okay. Oh, the probability of not A is 99. Yeah. Okay, 0.99. Yeah. Okay, so we get the complement event. It's probably a good idea to put those in there as well. Okay, so the probability of A bar is 0.99. Good. All right, let's go up to a false negative. Okay, so if a person has cancer, there's a 10% chance they will test the other way. Okay, the wrong way. 90% chance that they'll test the right way. How can we write that mathematically? What do we know from this? The probability of B is, okay, the probability of B, the probability that X tests positive is 0.9. I think we got to get 0.9 in there. They test positive, but it's more than just that, right? It's more than that they test positive. It's that they test positive. B intersect A. No, it's not B intersect A, but B given A, yeah. So the probability they test positive if they have cancer is 0.9. Okay, the probability that they test positive is not 0.9. Probability that they test positive, given that they have cancer, is 0.9. And likewise, we can do the complement event here. The probability that they test negative, given that they have cancer, is 0.1. Yeah? Okay, so if a person doesn't have cancer, okay, so we'll just fill those things in. So if they don't have cancer, that's A bar, okay, and then they test positive, that's 0.05, and the probability they test negative when they don't have cancer is 95. Okay, and that's just using the complement rule. Okay, so these are all the things that we know in the problem, yeah? Okay, next step, draw the probability tree. Okay, I'll get you started on this. Okay, so we start off in the universe where a person is either dealt a cancerous hand or a non-cancerous hand. Okay, so we'll put cancer on the left as 1%, cancer, no cancer is 0.99. And then we have, they either test positive or negative. Let's just put positive on the left, negative on the right. Okay, so if they have cancer, and so there's a 90% chance it's going to return yes, 10% chance it's going to return no, and we'll likewise do positive and negative here. So no cancer should be 0.95, and yes cancer 0.05. Okay, so far so good. Okay, what's the thing that we need to calculate? What's the question asking us? All possibilities of them testing for cancer. I mean, I agree we're going to have to compute that number along the way, but that's not what the question is asking. Sorry. What's the probability of the person that, so what do we want? We want the probability of A? already know the probability of A. It's 0.01. So that's not it. It's the probability of A. Say it again. Conditioned by B, right? Given that they tested positive. Okay, so we have extra information here. It's not just that they. It's not just the 1% that they started with. Okay, so we are interested in where A and B are in this diagram. Let's mark that. That's one of the steps in the 4-step process, right? Okay, so the probability they have cancer. Where are the cancerous ones here? Everything on the left, right? Cancer is everything on this side. Okay, so those two arms give us A. And B is they tested positive. So that's this arm here on the cancerous end and this arm here. Okay, and if you're looking at what's here, probability of A given B, you need to find out where these two things overlap. So the probability of A intersect B divided by the probability of B. Okay, so we're just laying it all out here. And the probability of A intersection B is just this one arm, right? There's only one case where it overlaps. Okay, and we can multiply the arms here. So that's 0.01 times 0.9. Okay, so that's that arm. Probability of B is 2 of the arms. It's the same arm we just looked at and this arm here. So if we multiply those together, we get that, and we multiply these together, 0.99 times 0.05. Okay, you run these through the calculator, and you end up getting 15.4%. And that's a number that might surprise you, maybe. Maybe you expected a test that has this degree of accuracy to give you something a little bit more confident. Like you might be a little bit more confident the person has cancer. And it's just not the case, right? I mean, this is way more confident than when we started, right? So we started, it's just sort of a 1 in 100 type of thing. But this actually kind of makes sense if you think about like just the back of the envelope calculation, just for a moment. Okay, so let's just say we had like 10,000 people. Okay, so how many of them have cancer? Well, it's 1 in 100. So there's 100 people that have cancer, right? Everybody takes a cancer test. The 100 people, you get 90 positives, right? 90 positives. And of the 9,900 people that don't have cancer, you're actually going to get some positives there too, okay? Because there's some false positives. And 5% of 9,900 is, it's just a little less than 5% of 10,000, right? It's like around 500. It's 495, okay, if you want to be exact. But it's at a ratio of 90 to 500, and that's actually 15%. Okay, so 90 of those people that test positive are out of 590 basically have cancer. And if you've ever been involved with somebody that has cancer, I am. I've many people in my life. I play bridge. Lots of people are older. You tend to get a little bit more cancer when you're older. But even if you test positive for cancer, they don't tell you right away. They say you declare that you have cancer, right? Because this is not a very, you wouldn't stake your life on this number. So they usually say something like, we should have another test. And the more independent tests you have, the more confident this number becomes. It actually starts to amplify quite a bit. Like I think if you do the same sort of test again, you end up getting something like 80%, and that becomes in the 90s and so on. Okay, so bedside manner is important. You don't want to freak out people just because you got one positive test result. Okay? So you definitely want not just one second opinion, but a second and a third and a fourth opinion as well. Okay, all right. So we've been doing these sorts of conditional probability problems. This is supposed to be like a end of unit type of slide, but it could be a review slide as well. Let's just quickly go through where we've been. We started off by talking about random processes, and when we're talking about math, maybe it's better for us to talk about computer code instead as a process. And I have written out a bunch of computer code, and you should maybe think about doing that as well, okay, when you want to be explicit about the process. There are two functions that behave independently from trial to trial, Bernoulli and Randint, okay, and they do the expected things. We draw out a probability tree. You compute the probability of an outcome, which is a leaf, by taking the product of all the probabilities along the path. And then you collect all the things that fall into each bucket, each event, and by just identifying them in the tree. It makes it a lot easier to visualize what's going on, okay? Or at least you won't fall into any mind trap along the way, and there are some dangerous mind traps that might occur. Conditional probability is basically changing the sample space from the universe to a smaller universe B. You take the overlap in probability as a fraction. Interestingly, if you decided to cross-multiply this, you would end up getting the probability of A given B times the probability of B equals the probability of A intersect B. And this is actually the multiplicative rule down here, but just for two sets. Okay, so I state the multiplicative rule as a whole bunch of events happening all at once. So given that A occurs and B and A1 and A2 and A3 and AK, it's the probability of A1 times the probability of A2 given that A1 occurred. Okay, that's exactly what's written up here, except B is A1, I guess, in this thing. Okay, this is actually an explanation of why you can take the product of probabilities along the path. I sort of crash coursed it so that you could do your second assignment. So I gave like one slide and said, this is you multiply. You just believe me, you multiply. This is the reason why. Okay, it's this conditional probability thing. Okay, now why is that the case? I'm just going to go back to one example, and you'll see what I mean. Just in the way that the language occurs. Okay, so I guess we don't need that anymore. Okay, so back to this example. We're following paths about wins and losses. All right, wins and losses. If you imagined, okay, that each event along here was A1, A2, and A3. A1 would be the event of a win on game 1. And then A2 would be a win on game 2. So we'll just say AI is event of win on game I. Okay, so those are the events. Well, if we were to look at the probability of, well, let's just shorten this thing down a little bit. So win, maybe win, loss, win. Okay, so that would be A1 intersect A2, A2 bar intersect A3. Okay, all right, I'll just write that. Why not? Okay, so that represents win, loss, win. So that represents this path here. And I say that you multiply those things together, right? Okay, so here's why. So it's the probability that you win the first game. That's a half, right? That's a half. And then times the probability that you you lose the second game, A2 bar, given that you won the first game. Okay, so that's a third. That represents this. So you went down this arm, so you know what A1 occurred already, so now you're looking at A2. Okay, so that's a third. Times the probability, and then you do I guess it's A3 given A2 bar intersect A1. Okay, and that's also a third. Okay, so that's that third one, given that you won the first game and you lost the second game. Okay, so given that those two things. So you're just following the arms down the tree, given where you've already been. Okay, so it's given all of those past events, and they're just accumulated in those brackets. Okay, so this is why the multiplicative event works, multiplicative rule works, is that you're combining events as your chain down the tree in this. It has an if. There's an if implicitly built in. Okay, we have more examples to do, and without further ado, we are going to do the Monty Hall problem. Okay, some of you have seen the Monty Hall problem before, and if you have not or never heard of Monty Hall was a game show host for a sort of seminal game show from the 60s and 70s called Let's Make a Deal, and it was great. It was these sort of it was like at a circus there would be like a sideshow fast talker or hustler, and that was the game. There was always trading. Would you like to trade this for this? And if you did well, then you traded. You ended up getting a good prize like a car or a furniture set, and if not, you ended up with a bad prize like a goat, a zonk, if you will. Sometimes it actually was a goat. I don't know if you actually would be able to take the goat home. But anyway, it was famous for having doors and boxes, and in one of them, you have 3 doors. I think the original game show, they had numbered doors, but I'm using letters because it's easier for us when we write out the solution. We're going to do a demonstration of this now. I brought doors. This is the best I can do. I brought boxes. And here's how the game works, all right? So in one of the boxes behind one of the doors is a prize, okay? It's behind A, B, or C. The other two contain nothing or a bad prize. And after choosing your door, Monty reveals a door which does not contain the prize and then offers you to switch. And this is sort of the fun part of it all, was that the audience would sort of, egg you on and you sort of felt like you were getting conned, okay? So this has been phrased in magazines, both mathematical and popular, and it has some pitfalls. So I'm just going to write out the assumptions that we're going to use today so that we don't succumb to any of the other assumptions that people often make. First is the prize is equally likely to be behind any door. Second, you are equally likely to pick the right door. Third is that Monty always reveals a bad door, okay? So, and this is a common thing people get hung up on, is that, why doesn't he just screw you if you pick the wrong door? And so the host must open a door without prize. And last, if the host has a choice, it's 50-50 which door he opens. Okay, so I'll give you a moment to get all those down. Sorry, this one here? Oh, sorry, that's open. My bad handwriting. Thanks. Yeah. Right. So yeah. So if you happen to pick the correct door right away, Monty can open either door and reveal a bad prize. And this basically says he'll toss a coin and open either door with equal probability. Okay. Yeah. No. So he can't reveal the door that you have picked. Okay. So yeah, it's you're always in a position where you are going to be able to keep your door or switch. Okay. Is it all clear? Should we play? Yeah, let's play. All right, need a volunteer. Who's going to play? All right. What's your name? Max. All right, Max. Pick a door, or pick a box. Middle box, B. All right, Max. Max says B. And all the prizes here were predetermined by random number generation. I had no say in the matter. I just did what the computer told me. Okay. So the computer also told me A doesn't have anything. Well, it has a lifesaver. Dodged a bullet there. Okay, so A is gone. All right. It's time for you to vote. Because, if this is a real game show, you guys are going to be shouting out what you want Max to do. And Max has 3 options. Switch, keep, or it doesn't matter because it's 50-50. Okay, I'll let you think about it for a moment. I got a little snacky for later. Ooh. Okay, you ready? All right, let's vote. Who thinks he should switch? Leave them up nice and high so I can count them. Who thinks he should keep? Someone? Who thinks it doesn't matter? It's 50-50. All right. Well, you saw what the vote was. Do you have a decision? Switch? All right. That's the one you wanted. All right. Before we open the boxes, let's do the math, shall we? Okay, we're going to draw a very big probability tree. Very big. Okay, there are 3 steps. The prize is placed. There are 3 places where it can go. Max picks a door. And Monty, me, opens the door. Okay, so it's going to create a triple. Okay, so a triple, an ordered triple. Okay, and I'm going to draw the tree on its side because, well, it's a big tree. Okay, so we'll start down here, and we'll go kind of up there, and here, and then get this one down here. I know that's off the page, but you'll live. Okay, so this will be A, B, and C for the first step. So this is the prize location. And in the case it's behind A, again, there are 3 possible choices. Right? It's so this is what Max picks. So this is A, B, and C. And each one of these will generate a B and C, and similarly down here. And of course, the probabilities of each of these is a third, because they're all equally likely. Okay, 9 different games. I got 9. Sorry, 27 is going to be the next. Except it's not going to be the entire next, right? Okay, so the universe that we live in, how do I want to organize this? Let's just do each one. All right, so so if a prize location is behind A and Max picks A, Monty can reveal either one. Okay, so this is reveal door. Okay, so Monty can reveal either B or C with probability a half. If it's behind A and Max picks B, Monty can only do one thing. He can reveal C, and similarly, he can only reveal B here. Okay, so there's some things missing, And because we have only one arm coming out here, what's the probability? It's 1, right? It's certain. Okay, so each of those is 1. And so we get all these events coming out here. Okay, so I'm just going to do the one up here. So it's 1/18th, 1/18th, and it's 1/9th, and 1/9th. Does that add up to a third? It does. Okay, so that's good. And we're going to do the same for each of these arms. Okay, so the only case where there's branching is where Max actually picks the door, or the box, I guess. Sorry, it could be A or C, but here it's going to be A, and here it's going to be C. Okay, so there's half and half here. So again, it'll be a 9th and a 9th, and 18th and 18th. Okay, and almost there. So the only branching we get is if Max picks the door. So it could be A, B. Okay, I'll give you a moment to catch up. Sorry. Okay, so most of you thought that switching would win. I mean, you know, the chances that Max picked the right door initially is 1 in 3. Certainly, we would like to do better than 1 in 3. I don't think it can be worse than 1 in 3. And with all this extra information, hopefully it's much better than 50-50. So switching or keeping sounds like it's going to matter. And you all think that switching is the best, so let's analyze that. So let E be the event that switching wins. Okay, so Max, we live in the universe where you picked B. Okay, so, and door A was opened. Okay, so door A was opened, is here and here, right? There's actually, if the prize location is A, Monty can't open door A, right? So there's no arm that's up there. Okay, so we are interested in the probability of winning by switching. If B was picked and A was open. Okay, which is what happened here. Okay, and just mathematically, this is the probability of E, and B was picked and A was opened, divided by the probability that B was picked and A was opened. Okay, and if we look at these two cases, there's only two, right? It's BBA or CBA, and it's, let's see, it's looking like switching is a win 1/9 of the time versus 1/9 plus 1/18. Okay, so it's these two are going to be on the denominator, and just the bottom one is going to be on the numerator. Okay, so it's the probability of CBA divided by the probability of CBA and BBA. Okay, so there are only two universes after we've looked at the tree, right? There's a whole bunch of 20, well, not 27 arms, some of them got culled, but yeah, it looks like there's 12 arms, I guess, and only 2 of them are relevant to our discussion, right? CBA and BBA. Okay, so CBA has got probability of 1/9, and BBA has got probability of 1/18. 1/9 plus 1/18 is, let's see, 3/18, and this is 2/18, so this will be 2/3. Okay, which is better than a half. Okay, Max, given this analysis, are you happy with your choice, or do you want to switch? Sorry? You'll switch? You want box B back? You switched already. You're happy with box C? All right. All right. Air Canada pretzels. Where did I get those from? Air Canada. Yeah, so there you go. Max, you're a good sport. This is the bag of Toblerone. This is unfortunate that you picked the right door to begin with, but sorry, that's the way it goes sometimes. All right. Anyway, give Max a hand for being a good sport there. All right. We got there. Okay, any questions about this example? Some people find this a little confusing. There's an alternate version of this where there's 100 doors and 99 of them have no prize. It's even much more, stark when they open up 98 of the wrong doors, and the odds of you picking the wrong door initially, you actually take the complement of that. So that's the generalization of this. So your chances of picking the right door right away is 1 in 3. Unlucky today, but the complement is 2 in 3. Yeah. How come we don't put both events on the top? Oh, because, okay, so why don't we put BB up there? We are interested in the event that E wins by switching, right? E is winning by switching. So he wins by switching his doors. If the prize was in C, he picked B and A was revealed. Okay. Okay, so he wins in that one case, but not in this case up here. Yeah, so that's why it's up there. Yeah, so if he kept, then it would be 1/18 over 1/9 plus 1/18. Yeah. All right, good. Let's look at some conditioning rules. Okay, so some questions for you. Suppose you have events A, B, and C. If A is a subset of B, then what if you condition both on C? Okay, so they would normally say probability of A is less than or equal to the probability of B. What if you condition both on C? Does the monotonicity rule still hold? What do you think? Okay, maybe this is a good day for voting. Maybe we should vote these down. Should we do that? Let democracy rule? Yeah, all right, let's do it. Okay, so do you think this is true or false in general, that the probability of A given C is less than or equal to the probability of B given C if A is a subset of B? Prepare to vote. Ready? Okay, let's vote. Who thinks it's true? Who thinks it's false? Okay, majority rules. It's true. Okay, now why is it true? Well, if we were to draw a C in this diagram, okay, so let's say this is C, okay, and we did some shading. The probability of A given C is the stuff that overlaps. And you can see that the overlap of A with C is contained within the overlap of B with C. Okay, so we suspect that this is true because A intersects C is a subset of B intersects C. Here's a quick proof. The probability of A intersects C, well, that's defined to be the probability of A intersects C divided by the probability of C. And because A intersects C is a subset of B intersects C, because A is a subset of B, this is less than or equal to the probability of B intersects C. Okay, so this is by monotonicity. Sorry, I'm writing this wrong. Okay, so we just use the monotonicity on that one step, but the denominator is still the same, and that is the probability of B given C. Okay, let's do the next one. So if the probability of A equals the probability of B, then do the probabilities of A and B still hold equality if you condition on C? Prepare to vote. Okay, ready? Okay, let's vote. Who thinks this is true? Who thinks this is false? Why is it false? Yeah, C could be, C could be A, right? It all depends on how C overlaps each of them. Okay, so again, just using the Venn diagram in the corner, here the overlap with A is kind of tiny compared to B, and we just don't know. Okay, you did a problem like this on your first assignment, except I didn't tell you it was conditional probability, but you were dividing things by the probability of C, a third event. I don't know if you remember doing this problem. Maybe you didn't. You had options. But we suspect no. I used inequalities, I think, but the inequality can flip. Anyway, maybe you remember what we did. Anyway, C might overlap B more strongly than A. And you did something like this on assignment 1. Okay, and the counterexample that was given was let A equals C, where A and B are disjoint. Okay, so then the probability of A given C is 1, and the probability of B given C is 0. Okay, so just because they're equal outside doesn't necessarily mean that when you condition on them they're going to maintain their equality or inequality, as was done on assignment 1. Okay, what about inclusion, exclusion? Prepare to vote. Ready? Okay, let's vote. Who thinks it's true? Who thinks it's false? You weren't ready. Prepare to vote. Ready? More ready? All right, let's vote. Who thinks it's true? Who thinks it's false? Okay, a few dissenting people think it's false. This one's true. If you draw the diagram, again, I'm sort of drawing C in the corner. I'm not going to shade the entire thing. I'm just going to shade the portion that overlaps B. Okay, so I'm going to shade it blue, as I always do. Okay, and then I'm going to shade a yellow. And here we're looking at the portion that overlaps with C is A intersects C, the portion that overlaps with B is B intersects C, and the portion that overlaps all three is A intersect B intersects C. Each of those regions can be parsed out to be into its disjoint components, and because the denominator is the same, it actually works. And so we suspect yes, because A union B intersects C, these three regions that are colored is actually the union of three disjoint sets, and they're the same disjoint sets that we did when we proved this originally. But they each have an extra C in tow. Okay, the proof would be exactly the same. And in fact, any rules that were based on set theory, that we developed that were based on set theory, so inclusion exclusion was based on set theory, monotonicity was based on set theory, complement, difference, and union bound, all of those still work if you condition. Okay, so we suspect also difference rule, complement rule, and union bound. They all should hold, okay, as long as you condition on the same thing. If you condition on different things, it's probably not going to work, okay? So just be warned about this, that when you put something after the bar that's not the same, it's probably not going to work. In fact, B intersect, this is all very dangerous in a way, like B intersect C might be disjoint, it might give you 0 in the denominator. That's probably not so good anyway. But usually conditioning on different things doesn't hold. Okay, so this is like inclusion, exclusion, but on the conditioning part, yeah, don't do that. Okay, condition on the same thing if you're going to do anything at all. Here's a good one for you. What does it mean if the probability of A given B equals the probability of A? Do you have any intuition for this? Maybe B is a subset of A. It might be, but that is not as general as what I was going for. B is the universe, so that would be like a superset of A. Yeah, you said the same thing as... Sorry? The probability of B is 1. That might occur, but there are other situations where the same thing occurs. Okay, so you'll notice that the probability doesn't change even though you have the extra information B. Okay, so given that you knew B, it didn't actually affect the probability. Okay, this means that A does not depend on B. Okay, A does not depend on B has a funny term, it's called independence.